Today we're diving deep into deep reinforcement learning, the secret sauce behind AI that learns to win games through pure try and error. Let's start with the basics. Imagine you're an AI agent and you're dropped into this simple grid world. You start at the top left corner, you're the blue sphere. Your mission, navigate to the yellow boxes in the corners while avoiding the walls and obstacles. Here's how the game works. Reach the boxes, you get 100 points. Hit a wall, you lose 10 points. Every step you take, you lose 1 point. So you want to get there fast and avoid obstacles. Simple enough, right? But here's the catch. You have no idea about what any of the squares do. You have to figure it out by exploring. Now, there are different ways an AI can approach this challenge. Think of them as different learning strategies. Pure learning is like making a strategy game. It learns the value of every action in every situation through trial and error. Deep Q networks are just Q learning with a brain upgrade. Instead of memorizing every situation, they learn patterns to handle complex games with millions of possibilities. Policy gradient, this method skips the value calculations entirely and directly learn the strategy, what action to take in each situation. We'll see how they all connect to the same core idea. Every AI learning system has 4 key ingredients. First, state. Where you are right now, in our grid, that's your position. Second, action. What you can do, you can move up, down, left or right. Third, reward. The feedback you get. Did you just hit a wall? That's minus 10 points. Fourth, next state. Where you end up after your action. The AI job is simple. Learning which actions to take in each state to maximize reward. But how do we teach a computer to do this? After the Q function, think of Q as standing for quality. It answers the question, how good is this action in this situation? Q of S and A gives us a score for taking action. A instead S. Higher scores mean better action. For example, Q of position 1 and you want to move to the right is A 5.2. Q of position 1 and you want to move up 23 or 1. The AI simply picks the action with the highest Q value. Easy. Initially, we can store these Q values in a simple table. 1 row for each position, 1 column for each action. The AI starts with random values, then updates them as it explores. If moving right from position 00 leads to good things, that Q value goes up. If it leads to a wall, it goes down. It's essentially creating a strategy guide that says, when you're here, do this action. But how do we actually calculate these Q values? That's where the Bellman equation comes in. It's the heart of reinforcement learning. Q of S and A equals immediate reward plus discounted future value. Let me break this down. You get some immediate reward for your action. Plus you get the value of wherever you end up next. But future rewards are worth slightly less. That's the discount factor. It's like saying, this action is good if it gives me points now and put me in a good position for later. Here's how the AI actually learns. Let's say current Q value for an action is 20. AI tries the action and gets reward plus 5. Best possible future value 30. Target value 5 plus 0.9 times 30 equals 32. The AI sees its prediction was too low, 20 versus 32, so it nudges the Q value up toward 32. This happens millions of times until the AI gets really good at predicting. Now here's the problem. Our simple grid has 16 positions. Easy to store in a table, but real games, chess has 10 to the power of 43 possible positions. Go has 10 to the power of 170 possible positions. Atari games, millions of pixels. You'd need a table bigger than the universe to store all those Q values. Enter deep Q networks, or DQNs. Instead of storing Q values in a giant table, we use neural network to approximate them. Think of it like this. Instead of memorizing every possible chess position, You learn the patterns that make positions good or bad. The network takes in the current state and outputs Q values for each possible action. This is huge. Now we can handle games with virtually unlimited complexity. But there's another approach. Instead of learning Q values and then choosing actions, what if we directly learn a policy? A strategy that tells us what to do in each situation. That's policy learning. Instead of asking how good is this action, we ask what should I do right now? Both approaches work, and modern AI often combines them. The best of both worlds is called actor-critic. The actor is the policy. It decides what action to take. The critic evaluates how good the current situation is. They work together. The critic provides feedback to help the actor improve. It's like having a coach training a player. And this is how we get AI that dominates in 2025. ChatGPT and LLMs, deep reinforcement learning powers the conversational AI you use daily through reinforcement learning with human feedback, making them helpful. In gaming, AI agents are mastering complex games like Red Dead Redemption 2. Autonomous systems, self-driving cars and robots learning complex manipulation tasks. Recommendation systems, your Netflix, YouTube, and social media feeds are optimized using these same principles, all using the same core idea, but now it's everywhere. So there you have it, the math behind every deep RL. From simple grid worlds to powering ChatGPT, from beating Go champions to thriving your recommendations, it all comes down to this: AI that learns by trying, failing, and getting better, just like us, but millions of times faster. The future isn't just about AI beating games, it's about AI learning to help us in everything we do. What do you think AI will master next? Hit like and subscribe if you enjoyed this.